Okay, we're going to start doing some chapter 15 examples. So let's look at the first one here. You can find these questions in your textbook. They do these demo examples for you within the actual text itself. Okay, so what we're going to do here is we're going to go through the steps, kind of explaining them in case you're not finding it helpful to have just the words from the textbook there. So we're going to start here, calculating some average rates and rates of change. So just write this problem down so that you can try it. And like always, I think you should, pause the video at this point and try them on your own before you watch me do it. Usually because that's just going to give you the better results. All right, so I'm going to pause this and write down some of this info real quick. I'll be right back. Okay, so the first question that we have to look at here is how we are going to calculate the average rate of change for the reaction here. All right, and now what we want to remember, and the reason they gave us this balanced equation, is that our average rate of change, we can link it back to this balanced equation. Okay, so we know that the rate is going to be equal to 1 over whatever the coefficient is in the balanced equation of the specific material that we're looking at. So here we're focusing on the iodide ions rather. There's a 3 in front of that. Okay, so it's going to be 1 over the coefficient of 3 because there's a 3 in front of the I minus here. Okay, we also notice that our I minus is a reactant. Okay, and because our reactants are going to be decreasing in concentration and our products are going to be increasing in concentration, we're going to put a negative sign in front of the 1. Okay, so we're using this fraction here to relate the reactants and the products to one another using their position in the reaction and the coefficient that's in front in the balanced equation. All right. The next part of this relationship is going to represent the rate of change of the particular component. Okay. And our rate of change is going to be represented as the delta concentration value. So in this case, it's going to be delta I minus divided by the change in time, delta T. Okay, so once we have these two things set up, now we can kind of plug in the information that we have from the problem and figure out what the rate is going to be. So we'll keep our -1, and we're going to multiply that by the change in the concentration of iodine. And that delta symbol is always going to be final minus initial. So in this case, it's going to be final concentration minus the initial concentration. Okay, and we're going to divide that by the change in time, the final time minus the initial time. So we'll take that 3 and carry it over here. And it's going to be 10 seconds, which was our final time, minus 0 seconds, which was our initial time. Okay, and this is going to give us our rate. So our rate is going to be 4.40 times 10 to the -3. And our units here are given in this, when we solve this problem, right? We have molarity on top and seconds on the bottom here. So we have molarity over seconds as our unit here for rate. Once we know the rate of the average rate of the reaction here during this time period, we can figure out what the rate of change of each of the components are. Okay, because the average rate of change should be the average for all of them. All right, so in the second part of the problem in B, when it says determine the rate of change in the concentration of the hydrogen ions, well, the rate of the hydrogen ions, the rate is going to be the same rather, except when we plug in this part here, our rate of change part, we're going to use the information for our hydrogen ions instead. Okay, so our hydrogen ion is a reactant, so there's going to be a negative sign in front of the 1. The number on the bottom, though, isn't going to be a 3 anymore. going to be a 2. Okay, and our deltas here are going to be in relation to the hydrogen ion instead of the iodide ion. Okay, and this is asking us to solve for the rate of change in the concentration of the hydrogen ion. And that term you want to specifically link to this expression here. Okay, so this delta H plus over delta T, this is what we're talking about when we're saying the rate of change in concentration. Spell that right, Lauren. Okay, so that's the rate of change in concentration. Now, the good part is because we already figured out what the average rate of change is, we have a value that we can plug in here for rate. Okay, and we can then solve that expression specifically for delta H over delta T. And delta H over delta T is what we're talking about when we say the rate of change in concentration. All right, so if we set this up, we have 4.40 times 10 to the negative 3 molarity over seconds. And that's going to equal negative 1 over 2 delta H plus over delta T. Okay, and now I'm going to just use some algebra to isolate this term. Okay, so I'm going to multiply this side by 2 over negative 1, and I'm going to multiply this side 2 over negative 1. All right, and the average rate of change I'm going to get for the hydrogen is going to be, let's just arrow this over, negative 8.80 times 10 to the negative 3 molarity over seconds, and that is going to equal the rate of change in the concentration of your hydrogen ions. Okay, so this is going to be our average rate of change for the reaction, okay, linked to a specific time interval that we're looking at. And what we solve for here is the rate of change in concentration of one of the specific components of the reaction. All right. Now in part 2 of that question, hold on one second. It asked us to look at the H2O2 and the I3 minus. I'm assuming that you can just ignore the dogs barking. We are going to use the same rate though for this. Okay, but now we're going to be looking at the H2O2 and I3 minus. So we're going to find their rates of change in concentration. But we go about it the same way. Okay, so once you can identify what these terms are, like what they mean, then it's really easy to solve for them. We still have a rate that we're working with right off the bat. Okay, so we're going to focus in on the H2O2 first. We know that the rate's going to be equal to negative 1 over 1, and then delta H2O2 over delta T. Okay, and again, this is the rate of change in concentration, so we're just going to isolate this term. So we have 4.40 times 10 to the negative 3 molarity over seconds. Okay, and obviously we see that we're multiplying both sides by negative 1, basically. But this should make sense because H2O2 is a reactant, so its rate of change in concentration should be a negative value because we're losing some of the H2O2. So its rate of change, because its coefficient in front of the balanced equation is 1, is just going to be the negative value of the rate. So it's going to be negative 4.40 times 10 to the negative 3 molarity over seconds. Okay. The last example is the I3 minus, and over here we have a product, but we have a product with a coefficient of 1 out front. So the only thing that's going to be different here is that we have positive 1 over 1. Okay, so if we take our rate and we plug in our 4.40 times 10 to the negative 3 molarity over seconds, then we multiply both sides by positive 1. I mean, I'm not even going to do that. I'm not writing that out. But we see that our delta I3 minus over delta T in this case is going to be equal to positive 4.40 times 10 to the negative 3 molarity over seconds. So we have a positive rate of concentration change value for our product here. All right, I'm going to erase this and pull up the next one. Okay, so in this question, we're going to tackle how to figure out the orders of the different reactants and figure out what the rate law is and find the K, which is our rate constant from that data. So both of these questions are very similar. Okay, so we'll tackle one at a time. But take a minute to copy them all down because I'm going to pull this off of the screen in a minute. But you're going to see that the process here is going to be very similar for both of these. All right, and let me pull up the little laser dot guy. Before you can figure out what the rate law for the reaction is, you need to figure out what the order values for each of your reactants are. Okay, hopefully that those terms make some sense from what you read about already. But you should know that when you're looking at rate laws, you need to figure out, the rate law is going to consist of the rate constant, the concentrations of each of the reactants, and then those reactant orders. And we can use tabulated data, like what's given over here, to help us figure out what the orders of those reactants are. Okay. This particular experiment has 4 trials in it. Okay, and in the trials, we're looking at different concentration values for each of our reactants, and we're only focused on the reactant values here. And when we change the concentrations of these reactants, you see how it's going to have an effect on the rate, the corresponding rate. Okay, so when we're looking to figure out what the orders are, I just want to focus on this before I turn this off because you have to be able to pull out the trials that you want to focus on to calculate the orders. When you're trying to figure out what the order is for example, your NO2 gas, you need to use the trials that have different NO2 values, okay, and where the CO values do not change. All right, so you see in trials 1, 2, and 4, each of these have a different NO2 value. In those 3 trials, we see that our CO value remains 0.10, 0.10, and 0.10. That's a very important step. You cannot miss that step of choosing the correct trials to compare in order to find the orders for your reaction. Okay, so when we're finding the order for NO2, we want the NO2 values to change, and we don't want CO values to change. When we want to find the order for CO, we want the CO values to change, and we want the NO2 values to stay the same. All right. So keeping that in mind, let's actually solve the problem. So first, we're going to write out what our general rate law is going to look like. okay? So it's going to be rate equals K, which is our rate constant, times the concentration of the NO2, and we're going to say it's raised to the M. That's going to represent the order of this reactant, times the concentration of CO raised to the N, and the N will correspond to the order of the CO. All right. Now we have to find the M and N values so that we can write out the rate law, right? We can't write out the rate law until we know these two values. So for NO2, we can use trials 1, 2, or 4 in order to figure out what M is. It doesn't matter which two you pick, but you have to pick two of these. And we're going to take those. I'm going to use 1 and 2, and we're going to set up a way to solve for our missing order value. Okay, so we're going to take the entire rate expression for reaction 2 and divide it for the entire rate expression of reaction 1. So rate 2 is going to be equal to K times the concentration of NO2. I'm going to write it out like this first, just so we can just so you can see it a little bit. This concentration value for NO2 is going to be specific to trial 2 times the concentration of CO for trial 2. And we're going to divide that by rate 1 times K. And this is going to be for trial 1. Okay, I've put it rate 2 over rate 1. If you solve it as rate 1 over rate 2, you're still going to get the same answer. If you chose trials 1 and 4, you're still going to get the same value for M. If you choose trials 2 and 4, you're still going to get the same value for M. Okay. What's important is, in this case, that our NO2 values change between the two trials and our CO values are the same. Okay. Because watch what's going to happen here. So rate 2 is 0.0082. And rate 1 is 0.0021. In trial 2, our NO2 is going to be 0.20 molar. In trial 1, our NO2 concentration is going to be 0.10 molar. In trial 2, our CO concentration is 0.10. And in trial 1, our CO concentration is 0.10. Let's put a little molar there. Okay, when you compare these now, you're going to you have to think about it like, what can cancel out of this expression? So K is a constant, right? So K is not going to change between trial 2 and trial 1. So because these K values are the same, if you divide two things that are the same value, they're going to be 1. So they're going to cancel out. 0.10 divided by 0.10 is going to be 1. So it's going to cancel out. These N values are the same. They're going to cancel out. So now what we're left with is this division. Okay, so if I do 0.0082 divided by 0.0021, I'm going to get 3.9. Okay, and that's going to be equal to 0.2 divided by 0.1 raised to the M. Okay, and I'm going to solve for this now. Okay, so I can rewrite this as 3.9 equals 2 to the M, because 0.20 divided by 0.10 is 2. Okay, and now when you have this exponent up here, we have to work on pulling the exponent off and solving for it. Okay, some people can look at this and they find it easy to solve for that just by looking at the relationship here. Okay, and that's fine if that's how you're going to do it. But you can use your logarithm or your natural logs to solve for the m variable. Okay, so if we take the natural log of both sides of this equation, because whatever you do to one side, you have to do to the other, we can rewrite that as the ln of 3.9 equals, when I take the natural log of this, I'm going to pull the exponent off and put it in front. So it's m times the ln of 2. So that's how you pull off exponents. Okay, you take the log of both sides or the natural log of both sides. And when you take the log or the natural log of a number with an exponent raised to it, that exponent gets pulled off and put in front. Okay, now we just have to solve for m. So you can put the ln of 3.9 into your calculator, and then you can divide it by the ln of 2. And that is going to give you your value for m. So when you do that, you're going to get 1.97. That's going to be your m value. And 1.97 is close enough to 2 where we can call this a second order reactant. Okay. So now back up here in your rate law, this rate law that we're building, we know that this value here, this m value, is going to be 2. All right. And now we have to do the same thing, but for the CO. We have to figure out what the n value is here. All right, now for the CO, we're going to have to use a different set of trials, because now we need a set of trials where our CO value changes and our NO2 values stay the same. And for the CO, that's going to be trials 2 and 3. Those are the only ones that meet those conditions here. Okay, so we're going to do rate 3 over rate 2. I like to put the bigger numbers on the top, so you're going to constantly see me putting, like, that's how I'm going to orient this, but again, it doesn't matter, as long as whatever rate is on top corresponds to the concentration values that belong with that trial. Okay, so for rate 3 over rate 2, that is going to be trial 0.20 and 0.20. And you can put this as a 2 or not. You can keep it as an M because it's going to cancel out anyway. But since we know what, I just put it in there. Then we're going to divide that by the concentrations from trial 2, where the NO2 is 0.20 and the CO is 0.10. Okay, so again, we're going to cancel out the things that are the same here. So our K values are the same, so they cancel out. The 0.20s are the same, they cancel out. These cancel out, and now we're left with this. Okay, 0.20 divided by 0.10 is 2. So this expression is going to be equal to 2 raised to the n. 0.0083 divided by 0.0082 is going to be 1.01. Okay. And now we're going to go through that same process of isolating the exponent here. All right, so we'll take the log or the natural log of both sides. Doesn't matter which one you use. Okay, now we'll divide both sides by the ln of 2. And remember that when you have the ln of a number divided by the ln of a different number, that you're going to put these in your calculator separately. So you have to literally do 1.01, take the ln of that, and then divide it by the ln of 2. All right, what this is going to give us is 0.017. And that's going to be our n value. So we're going to say that Carbon monoxide is going to be a 0 order reactant. Okay, so now for this N value up here, we know that it's 0. Okay. Now that we've done this, now we have a rate expression, a rate law for this, right? When you have a 0 order reactant, okay, anything that's raised to the 0 power is going to be 1. Okay, so because CO concentration raised to the 0 power is always going to be 1, it's going to kind of drop out of our overall rate law because its concentration is not going to have an effect on the rate. This is why 0 order reactants the concentration of them doesn't have an effect on the rate, because when you take that concentration value, regardless of what it is, and you raise it to the 0 power, it's always going to be 1. Okay, so our real rate law here is going to be that the rate is going to be equal to K, which is our rate constant, times the concentration of the NO2 squared. Okay, that's going to be our rate law. Once we have the rate law, then we're going to be able to use any of our trials to figure out what our rate constant is. Okay, and if you go through the different trials, you might get numbers that are very, very slightly different, but they're all going to be around the same thing. Okay, it doesn't matter which trial you pick. What's important is that whatever rate you use, you're using the corresponding NO2 concentration for that rate in order to solve for K. So let's use trial 4 because we haven't used that one yet. Okay, but you can actually go back and try it with the other trials if you just want to verify this for yourself. The rate for trial 4 is 0.033 molarity over seconds. That's going to be K times the concentration of NO2, which is 0.40 molar squared. And we'll divide both sides by 0.40 molar squared. Okay. And we get a value of 0.21. Pretty sure. Yeah, 0.21. Our molarity unit up top cancels out, and one of these molarities is going to cancel out down here. So we're going to be left with units of molarity inverse 1, seconds inverse 1. And that's going to be our K value, our rate constant for this reaction. All right. So we're going to jump in and look at that second one. You can go back and look at the slide with all the numbers on it if you want to remind yourself, but we're going to work through this one a little bit faster. We're doing the same thing. We're focused on the same thing here. So for this reaction, we're looking to find the rate law and the value of the rate constant. So we can write out our generic kind of format for the rate law first. Rate equals K times the concentration of CHCl3 raised to the M. And we're using M, N, and P here because that's kind of what your lab book uses. You can use A, B, and C. It doesn't matter what letters you assign to these order values. The only thing that matters is that you're consistently associating the letter you assign to the CHCl3, make sure that you consistently associate these two things. You don't want to be like switching it around and all of a sudden calling M like the chlorine gas or something like that. Okay, so what we got to find here. All right, so we're going to look here. Okay, I'm going to use trials 1 and 2 to find the order for the CHCl3. So rate 2 is 0.0069. Rate 1 is 0.0035. The CHCl3 is 0.020. This is 0.010. Okay, so we see what cancels out here. I don't know why I put that in my calculator. Anyway, 1.97 equals 2 to the m. So we're going to take the ln of 1.97 equals m times the ln of 2. I think you see where this is going. Okay. So you can put a little 1 up there. For the chlorine gas, we'll use trials 2 and 3 because in trials 2 and 3, our CHCl3 concentration stays at 0.020, but our chlorine gas concentration changes. So we'll do 0.0098 over 0.0069. Okay, so you see, when you write it out like this, it's also easy to see because you're going to have these two things that you don't care about solving for canceling out. And the thing that you want to solve for is the thing that's different. Okay, so here we have 0.0098 divided by 0.0069, 1.42. The molarity over seconds cancels out. Okay. So now we're going to have, let's write it over here so I don't run out of room. I'm going to take the ln of 1.42. And that's going to be n times the ln of 2. Okay, and we're going to get like 0.51 equals n here. So this is going to be one of our little special cases where we have a reaction order that's 1/2. You can write, yeah, I don't know, you can write 0.5 or you can write, like 1/2 when you put it up here. All right, I mean, in your textbook, we're going to focus on the properties of 0-order reactions, 1st-order reactions, and 2nd-order reactions, but there are other orders that exist. But we're going to focus specifically on the properties of those 3 types. So, if you're solving and you see like a half an order, don't be surprised because you might encounter things that aren't just 0, 1, and 2. Okay. Another thing that we can mention here, now that we've solved for this rate law, is what the overall order of this entire reaction is. And to solve for the overall order of a reaction, all you're going to do is add together the orders from each of the reactants. So the overall order of this reaction is going to be 1 plus 1/2 or 1/2. Okay. The overall order of our previous reaction was 2 plus 0. So it was, overall, it was a second order reaction. Okay. All right. Let's find K real quick, which we didn't do yet. We can use the fourth trial to find K since we have neglected it so far. Okay, so our rate for reaction 4 is 0.027. And that's going to be K times 0.040 times, oh, both of them are 0.040. Okay. And you're just going to be isolating there. So over 0.040. Just trying to look at these units. Molarity, molarity is 1/2. That's going to cancel out. So we're going to have seconds inverse 1 and molarity underneath. And that is going to be your K value. Okay. So pretty straightforward once you know how to do it. Let me pause this real quick and pull up the next question. So this question gives us a decomposition reaction, and it gives us another table of data, right? And so you're going to have some options here. You can look at the varying concentrations and try to work out the relationship between them like we were doing in the last one. Okay. And that might be what I end up doing here, because it's something I can show you on the board. But the other thing that you can do is you can set up a graph for yourself. Okay. And we're not going to use the graphical method too much in terms of like you creating the best straight line or anything like that, because, you know, we don't have you like submitting like Excel graphs and things like that. But you do need to know how to like recognize what will make a straight line in one of these graphs when we're looking at the different orders of the reactions. So what you're going to notice is that, sketch this out a little bit. Okay, when you're making yourself some kind of graph and you have, in this case, they're telling us to show that the reaction is first order. Okay, what we're going to see when our reactions are first order reactions, I want you to focus on what the axes are, okay? Because these axes, they change depending on the order of reaction you're looking at. So for a first order reaction, we're going to get our straight line when, hold on a second, excitable dogs. When the y-axis is the ln of SO2Cl2 in this case. And our x-axis is time. Okay. This is going to change depending on the type of reaction. All right. If it's a zero order reaction, then the y-axis is just going to be the concentration in this. Let's say we'll use SO2Cl2 as an example. Okay. If it was a second order reaction, then your y-axis would be 1 over the concentration of SO2Cl2. Okay, so what you can do is you can literally put in the data points that they gave you, and you can say, well, if I plug the concentration values and the time values in directly, does that give me a straight line? And you'll see that it doesn't. Then you're going to take all of the concentration values and take the natural logs of them. Okay, and then you can plot those values against time, and you'll say, does that give me a straight line? In this case, it does. If it didn't, though, then you would take 1 divided by the concentration of the SO2Cl2. Okay, and you get all those values, and you plot that against time. See if that gives you a straight line. One of them is going to give you a straight line. Okay, the one that gives you a straight line, that's the order of your reaction. So in this case, the natural log of the concentration versus time is what's going to give you that. All right. What else did this question ask for? Determine the rate constant for the reaction. Oh, okay, so that's another good thing. So let me pause this a second so I can go back to. All right, Leah, actually, let me pull this up for you here. Okay, I'm going to show you the graph that we made of this so we can talk about it. Okay, so you see here how we take the natural log of the SO2Cl2, okay, and we're plotting it against time, and now we have this straight line here. Well, what we're going to see is that our slope value, okay, it's a negative slope, and for your first order reactions, your first order reactants, the slope of that line is going to be equal to negative k. So being able to solve for the slope of that line is going to give you your k value. All right, that means that our rate constant here is going to be the positive value of this slope. So once you can plot that line and find the slope from the straight line, you're going to be able to figure out what that k value is directly. Okay, so that's easy enough, hopefully. We are going to use this now to find a different question, okay, or to find an answer to a different question. So in that last example, we figured out that that reaction was first order based on the graph, and we figured out its rate constant. So now if we carry out this reaction at the same temperature, and that's important because our rate constant is going to change if we change our temperature. But because we carry out the reaction at the same temperature, now we're going to be able to use that same rate constant of 2.9 times 10 to the negative 4 inverse seconds. Okay. If we know the initial concentration of the SO2Cl2, we want to know what the concentration is after 865 seconds has passed. All right, so let me go back to my screen. What this gets into is what is called the integrated rate law, okay? And you're going to be introduced to a chart by Professor Sheehan. It's also in your textbook. And that chart is going to show you the different half-lives, rate laws, and integrated rate laws for 0, first, and second order reactions. You have to know them and be familiar with them. And when you see a question that asks you to use your rate constant and figure out what your concentration change is after a certain amount of time has passed, that's like a red flag for you to use your integrated rate law. Okay, so we're going to look at the integrated rate law for our first order reaction. And that's going to be the ln of, no, I always put the bracket in the wrong place. It's ln of the concentration of A, and it has a little t here. I'm going to go through what these mean so that you can like talk yourself through this. Okay, so this ln of A sub t, we're talking here about the concentration after the time has passed. Okay, when you see the ln concentration of A with a little 0 down there, that's going to be your original concentration. All right, this K value is going to be your rate constant. And then this is going to be the amount of time that has passed. And what I'm going to tell you is that you need to make sure that your time is in the same units as your rate constant. Okay. In this case, that's fine because our K value here, just right over here, we've already determined that our K equals positive 2.90 times 10 to the negative 4 inverse seconds. And the time that we're focusing on here is also in seconds, right? It's 865 seconds. But if they had given you this time value in like minutes or hours or something like that, you would have wanted to go back and convert the time into seconds before you started plugging things into this problem. All right, so now we're going to plug in what we know, and we're going to figure out what the concentration is after that time has elapsed. Okay, so this is what we're solving for. Now we're going to plug in our rate constant. We're going to multiply it by our 865 seconds. Notice here that our units are going to be canceling out. Plus the ln of 0.0225 molar. Okay, so we're going to plug all this in our calculator. If you're having trouble using your TI-30 calculator still, you should go back and into Blackboard and watch some of those calculator videos that we posted, because they show you how to do a lot of the shortcuts here that'll make your life a lot easier. Oh, I didn't take the negative sign of that. Yeah, don't forget that. I just don't want to put it in my calculator. I just forgot to make this number negative before I multiplied it. Probably because I was talking to you while I was doing it. My bad. Okay, so we get negative 4.045. Okay, now we have to get rid of this natural log. All right, to get rid of the natural log, you're going to raise both sides to the E, and the E key or the E function is going to be linked to the natural log on your calculator. It's usually when you have to hit the second key to access it. So we're going to raise both sides to the E, and we get Oh, that's too low. Write it next to it. It's going to be 0.0175 molar. And that's going to be the amount of the SO2 Cl2 that's left after 865 seconds passes. Okay. All right. Let me pause this and get the next question up. All right, so here's another example. And notice the wording of this one, because now we're running into that situation that I discussed before where we have this rate constant, right? And the units of our rate constant are in terms of inverse seconds. And here they're giving us a time in minutes that we have to look at, right? Other than that, it's going to be a very similar process to what we just did. Okay, so this should seem nice and familiar to you. I wrote out some of the variables that we're going to be working with. They told us that it's a first order reaction, which is good. We didn't have to like solve for it or look at a chart to figure that out. So right away, we know which integrated rate law that we need to use to figure out the concentration value that we're looking for. Okay, but our first step here is going to be to take this time of 235 minutes and turn that into seconds so that our units will match up. Okay, so that's going to be pretty straightforward. Okay. 4 sig figs in there. Got that 0. Okay, and now we can plug in all of our values and we'll be able to solve for that pretty easily. Okay. So I'm going to put the minus inside my parentheses this time, so hopefully I don't forget about it. So it's going to be 3.36 times 10 to the negative 5 inverse seconds times 1.410 times 10 to the positive 4 seconds. So these will cancel out now. Plus the ln of our initial concentration, which is going to be 0.0445 molar. Okay, we get the ln of A little t equals negative 3.586. Okay, and so we're going to take, again, to get rid of this natural log, we're going to raise both sides to the e. So the concentration after some time has passed. It's going to be 0.0277 molar. Okay, if this were a zero order reaction, then you would have used the zero order integrated rate law. If it was a second order reaction, you would have used the second order integrated rate law. Okay, that's the only change you'd have to make there. All right, so let me pause this and pull up the next question. Okay, so take a look at these two questions. These are going to be dealing with half-lives, okay, and how we can use half-lives. The first question is asking us to find the half-life. The second question gives us the half-life and wants us to use that half-life value in order to find the rate constant so that we are able to determine a time value for a certain reaction, okay? So we'll sort through both of those. But the first question is very straightforward. It's asking us about the half-life of the reaction, and it is giving us the rate constant. The half-life formulas for each of the different types of reactions you should know. okay? First order, second order, and zero order all have different half-life formulas. Okay, so they told us here that we're looking at a first order reaction. They use first order for a lot of the demonstrations, but you should be just as comfortable doing a zero order calculation or a second order calculation. The only difference is that the actual half-life equation is going to be different. Okay, but for first order, for us to find the half-life, you're going to notice that the only thing that the half-life depends on in a first order reaction is the rate constant. Okay, so the formula for that is going to be 0.693 over K. Or another way to write that is that the half-life is going to be equal to the ln of 2 over K. But the ln of 2 is 0.693. That's why we end up writing it like this. Either way is acceptable though. But notice that they told us the K value in the first part of the question. They said that your rate constant is 0.271 inverse seconds. Okay, so they told us K. All we have to do is solve for the half-life. Extremely straightforward. So in this case, T1/2 is going to be 0.693 divided by 0.271 inverse seconds. And we're going to end up with a half-life of 2.56 seconds. Okay. The second question in this set is a little more interesting because it's not just a half-life calculation. They want us to use that half-life calculation and actually figure something else out. Okay. We're going to start with that same half-life formula though. They tell us in this case what the half-life is. They're saying that T1/2 is equal to 26.4 seconds. And then they want to know how long it's going to take for the concentration of a reaction to fall to 1/8 of its initial value. Okay, so we can think of our concentration initial as 1, right? So 1 means it's going to be whole. And our final concentration after some amount of time has passed is going to be 1/8. Right, so it starts at 1 and it ends at 1/8. Right? Now, if we have two concentration values that we're focused on, that integrated rate law should pop into your head. That's the way that we're going to be able to solve that. But to use the integrated rate law, right, if we write that out here, we need K. We can't solve the integrated rate law if we don't have K, right? And they're asking us how much time it would take for this transition to happen. Well, we can't have two unknowns, so we're going to need to find K before we can figure out the answer to this question. And we're going to use our half-life formula to do that, okay? Because we can rearrange this half-life formula and we can say that K is going to be equal to 0.693 divided by our half-life, right? And we know our half-life here because they told it to us in the problem, 26.4 seconds. All right, so now we have a K value. Now we have everything that we need to solve for this time value. Right, so we're going to say that our concentration of A after some time has passed is going to be 1/8. That's going to be equal to minus 0.0265 inverse seconds multiplied by some amount of time that we're going to solve for, plus the ln of 1. Okay. Now, it's pretty easy to take care of this section because the ln of 1 is going to be 0. So this will drop out here. So we're going to focus in over here. So we're going to divide both sides by negative 0.02625. Okay, and we get 79.2 seconds is the amount of time that would have to pass for us to go to 1/8 of our initial concentration. Okay, so you see, it's a very common way to present the information here, where they'll give you the half-life of your reaction and expect you to use that half-life to find your K value. And once you have that K value, now you can use that K value that you calculated as part of your integrated rate law and solve for whatever the missing component is. The missing component could be a concentration value, or it could be a time. Okay. But just, try to talk yourself through the steps of it so that you're not just looking at it and being like, well, I don't know how to approach this. There's too many unknown variables. Okay. There's always going to be a way for you to solve it. You just have to kind of talk yourself through the process. Okay. The more you talk yourself through the process, the more you're going to remember the steps. All right, so let's pull up the next question. All right, so these questions, the next 2 questions we're going to look at involve the use of the 2-point Arrhenius equation. And what we're going to notice, and I'll point it out when we get to when we're actually working through it, but what you're going to notice about the Arrhenius equation is that it looks a whole lot like the Clausius-Clapeyron equation that we had back in chapter 12. And you're going to notice that same relationship pop back up continuously throughout the rest of your chapters in 104. Okay, so we're going to see this kind of repeated. Here they're giving us 2 different rate constants and their corresponding temperatures. And we're going to use the relationship between rate constant and temperature to figure out the activation energy here. All right, the other thing that you can figure out is if you know the activation energy, you can figure out one of the other missing variables. Okay, so there's a relationship here between activation energy, temperature, and your rate constant. And that's what we're going to be focusing on here. So we're going to look at the different parts of this equation first. Okay. Our K values are obviously going to be our rate constants. Okay. And our T values are going to be temperatures. These temperatures have to be in Kelvin. You cannot plug Celsius or Fahrenheit temperatures into your Arrhenius equation. Okay. This value here is going to be your activation energy, and it's going to be generally given to you in terms of kilojoules per mole. Because your activation energy is usually given to you in terms of kilojoules per mole, I am going to recommend that you use a slightly different R constant than the one that they give you in your textbook. Okay, so we're going to write that one out here, and I'll explain why, and hopefully it will make sense. All right, so we have an R constant. You're going to see that your textbook tells you that your R constant is 8.314. And notice this is what it tells you, 8.314 joules over moles times Kelvin. That's what your textbook says. I am going to recommend that instead of using this R constant, that you use the kilojoules version of it. because then we have units of kilojoules over moles Kelvin, okay? And now you see we have matching units here, okay? I don't think that there's any reason to have a mismatch there. It just sets yourself up for confusion later on. You know, so that's my recommendation, and that's what I'm going to be using here. Now that we have that all laid out, now we can look at the information we were given in the problem and actually solve for it. They're telling us that the rate constant and they very nicely gave us temperature values in Kelvin already here. They said at 701 Kelvin, our rate constant is 2.57. Polarity inverse 1, seconds inverse 1. And then at 895 Kelvin, our rate constant is 567. Polarity inverse 1, seconds inverse 1. Okay, and we're going to be finding the activation energy. So we're basically going to fill in everything in this equation and find the activation energy in terms of kilojoules per mole. All right, it does not matter which K value you call K1 or K2. It doesn't matter which temperature value you call T1 or T2, except that the K value that you put on the denominator has to pair up with the temperature value that it corresponds to, the first temperature value here that corresponds from the problem. Okay, so whatever you call K1, whichever of these you call K1, that temperature has to be put first here. Whichever K value you call K2, that has to be listed second here. All right. So let's do that. So the ln of will be 567. I'm going to leave out the units because they're going to cancel out here. And that's going to equal EA over 8.314 times 10 to the negative 3 kilojoules over moles times Kelvin. So you see now we're going to get our EA value back in terms of kilojoules per mole, which is what we wanted. And then that's going to be multiplied by 1 over, again, if we have 2.57, that means 701 has to go here, minus 1 over 895 Kelvin. And you see our Kelvin units are going to cancel out here. So we're going to be left with this in terms of kilojoules per mole. I would recommend solving it out. Some people struggle with this type of solving here. It is a lot easier to think of, I'm gonna show you instead. I'm gonna solve out what's in here. Okay, that's gonna be my first step, and I'm gonna get a number for this. Okay, so I'm gonna kind of walk you through the process and walk you through how I would solve it if this part is confusing to you. So we have 1 divided by 701 minus, and I'm gonna put this in parentheses, 1 divided by 895, close parentheses. Okay, and I get this number. I'm going to erase this. Okay, this number that I get, I can put on the top of my fraction bar as something I'm going to multiply by my activation energy and then divide by this number here. Okay, because what we have here is EA over R times whatever this value is. Okay, now that I have a number for this value, I'm going to just put it up here so it can be multiplied by this term. So it's going to be 3.092 times 10 to the negative 4. Okay, I can erase that part. Okay, and it's going to be inverse Kelvin, so you see these little Kelvins are going to cancel out. When you write it out like this, I think that your next step becomes clear, okay? Because I can take the 567 divided by 2.57, take the natural log, and that's 5.396. I'm going to erase this and replace it with a number. 5.396. Okay, and I want to isolate the activation energy. Now this just looks like algebra because I'm going to multiply this side by 8.314 times 10 to the negative 3 kilojoules per mole, and divide it by 3.092 times 10 to the negative 4. I'm going to do the same thing over here. Okay, so 8.314 times 10 to the negative 3 times 5.396. Divided by 3.092 times 10 to the negative 4. Okay, and I get 145 kilojoules per mole as my activation energy. Okay. Sometimes you're given the activation energy and you're asked to solve for another component of it. That's what we're going to do in the next question. Let me just put this up so you can see it real quick. We're going to actually use the same reaction because now we have the activation energy value. And this question says, well, use the results from that previous example, and given the rate constants and temperatures from that example, as well as the activation energy we just found, predict what the rate constant would be for this reaction at 525 Kelvin instead. So they're giving us a new temperature to look at. Okay. Now, we're going to pretty much approach this the same way. It's just that now we have an activation energy and we're going to be missing one of these K values. Okay. So I should write that in here. I'll write the activation energy before I forget it. Okay, now it doesn't matter which piece of data that you use to solve this. Okay. Either one will work out. I'll use this one just because there's no decimals there, I guess. What I would recommend when you set this up, though, is that whatever your unknown is, you put it on the top of the fraction. It's just going to make it easier to solve later. So we're going to have the ln of K2 over 567 equals EA, which is 145 kilojoules per mole, over R, 8.314 times 10 to the negative 3 kilojoules over moles Kelvin. And then 1 over, if we have 567 here, we need 895 Kelvin here. And K2 is going to be 525 Kelvin. Okay. When you have everything filled in on the right side of your Arrhenius equation like we have here, I'd recommend getting good at putting it all into your calculator without writing it down separately. Okay, so like take your parentheses here. Okay, we have 1 divided by 895 minus, in parentheses, 1 divided by 525. All right, now take this value and without, clearing your calculator or anything, multiply it by 145 and then divide it by 8.314 times 10 to the negative 3. Because then you're not writing things down and making that, you introduce more room for error when you write things down and re-put it into your calculator. Now, once you get this value, if you want to go back and check it and write things down and put it back in and make sure your values match, that's a good idea. Okay, but I would definitely do at least one run through where you keep everything in your calculator and try to eliminate any possible error that might come. Okay, so here we have negative 13.73. Okay, and we don't have any units left over here because like everything cancels out. As we go through, our units here are going to come from this number. Okay, so we have ln of K2 over 567, molarity inverse 1, seconds inverse 1. And we want to get rid of this natural log. So we're going to raise both sides to the e so that we can cancel that out over here. That's another good thing about having this number already in your calculator, because now you can just go and hit the second E key and you'll get your value back out. I'm going to put it in scientific notation so it's easier to see. And we end up with K2 divided by 567 equals 1.086 times 10 to the negative 6. Okay, you see by doing that, now I've made it pretty easy for myself to solve this because I just have to multiply both sides by 567 to solve. Okay, so what I end up with is that my K2 value is going to be 6.16 times 10 to the negative 4, molarity inverse 1, seconds inverse 1. Okay, so 2-point Arrhenius equation. Not too bad, not too bad. All right, let's take a look at the last topic. All right, so take a look at this question. This is involving reaction mechanisms and figuring out rate laws based on these reaction mechanisms. So what we're given here is an overall reaction of ozone converting to oxygen. Okay, and they're telling us here that the experimentally observed rate law is this. Okay. Now, what we're being asked to prove is that this mechanism listed here is correct and consistent with the experimentally observed rate law. Okay, so we're proving that. So we're going to go through a few steps to prove that that's true. All right. The first step, or first thing that you're going to need to focus on doing when you're looking to prove that a mechanism is true is you need to look at this mechanism and you have to make sure that when you add the steps of the mechanism together, that you get the overall reaction back out. Okay, because if you don't, then you're dead in the water right away, right? To do that, you're just going to, I like to put a little plus sign there and like make it look like a math problem. Things that are on the same side of our reaction arrows that are the same species, they get added together, right? So we have O3 and O3, so that's going to be equal to 2 ozones. We have a singular oxygen on the reactant side here, and we have a singular oxygen on the product side of the first reaction. So we have the same species, but they're on opposite sides. So these are going to cancel out of our overall reaction. Okay, and then we have an oxygen gas in the first step and 2 oxygen gases in the second step. Those would be additive. Okay, so now we see that when we add these 2 mechanism steps together, we get our overall reaction back out. So our first kind of condition for making sure this mechanism works is met. Now, our second step is going to be to look at our rate determining step. Okay, your rate determining step is always going to be your slow step. Your slow step is always, hold on, I gotta spell that right, rate determining step. Your slow step is always going to be your rate determining step. I like to describe this to people like if you have a group of friends and you're walking from point A to point B, like it doesn't matter how fast of a walker you are. If you've got one slow friend, you all are only getting to your destination as fast as that slow person can go. Okay, that's the slow step. This is your rate determining step. It's going to determine how fast your reaction can proceed. It doesn't matter how quickly this conversion happens, because if this process is slow, this process is going to hold your rate up and make it take longer. Okay, so this is going to be our rate determining step. And your rate law is going to be based on your slow step. It's going to be based on your rate determining step. So you're going to actually write out a rate law based on this slow step. Okay. So according to our slow step, our rate law should be rate equals K times the concentration of O3 times the concentration of O. All right. Now the problem with this rate law though, is that it contains this singular oxygen here. And you notice how the singular oxygen is canceled out of our equation. We call that, we're going to pull these over here, something that gets crossed out of our mechanisms as we're adding the reactions together. This is called an intermediate. Okay, it only exists briefly and then it's converted into something else, but it does not exist in our overall reaction. Okay, that's what an intermediate is. And our rate law cannot contain an intermediate. Okay, it's okay if it's here initially, but we can't leave it like this. So what we have to do is figure out a different way to express what the concentration of a singular oxygen could mean, right? And what we're going to use is our first mechanism step, that fast step. That's going to help us do that. So this fast step here is going to give us a way, a different way to kind of express the value of a singular oxygen. All right, because we have a reaction here that goes, that's kind of in equilibrium, right? I'm gonna write this part over here, but I want to keep it separate from what we're doing over here. Okay, so when you see K1 forward and you have K -1 backwards, what that kind of means is that the rate for your forward reaction is going to be equal to the rate of your reverse reaction. Right? That's kind of like the definition of what equilibrium is, when the rate of your forward and reverse reactions end up equaling out, right? So the rate law for our forward reaction, we can express that as K times the concentration of O3, right? We can represent the rate of our reverse reaction as K times O2 times O, right? Because our reverse reaction is going in this direction. And we can call this K1 and we can call this K -1. All right. Now, what we want to do is find something that we can substitute in for this singular oxygen. Okay. So if I take this expression here and I can solve it for my singular oxygen, I'm going to have a way, I'm going to have an expression that does not use an intermediate that I can plug back in here to my rate law. Okay. So I'm going to divide both sides by K -1 times O2. And this gives me K1 over K -1, O3 over O2, and that's going to equal a singular oxygen. Now I can take this entire term, because I know that this term is equal to this value, and I can plug that in for this oxygen value. All right. So I'm going to rewrite this now with my new pieces plugged in. So rate is going to equal, we'll call this, let's just call it K2, because these are all the K1s. So we'll say K2 times O3. And now instead of O, we're going to write K1 times O3 over K minus 1 times O2. All right. And at this point, you've pretty much written a correct rate law, but we're going to clean this up a little bit. Okay, so we don't want to leave this because it looks a little messier like this. Now, the good part about K values is that they're constants. So the numerical value of them isn't really what's important here. So we can actually kind of create a new K value that's equal to K2 times K1 divided by K minus 1. Sorry, up there. I'm just going to call this K3. All right, so I'm going to say that K2 times K1 divided by K minus 1 is going to be equal to this new constant called K3. All right, and I'm going to put that out front. So rate's going to equal K3. O3 times O3 is O3 squared. So O3 squared. And that's going to be divided by O2. Okay. This is a finished rate law. The other way that you can write something, and we've seen this before, like when we have inverse seconds in our units, for example, when you have a term that's on the bottom of your fraction, you can express that as a negative exponent. Okay, so another way, another valid way that we can write this down is that rate equals K. I don't want to erase anything, but I'm also running out of room. K3 or K, it doesn't, you could just call it K if you want to, times O3 squared times O2 to the negative 1. Okay, so this term here or this term here, both of these terms that we solve for here are equivalent to this rate expression that we were given at the beginning. Okay, so we have just gone through the process of proving that this mechanism is a valid one. All right, I'm going to pull up one more example of this. And I really recommend trying this on your own before you watch me run through it, because people do get a little confused with the mechanism stuff. But if you just follow the steps, you know, like anything else, no big deal. Okay. So we're going to predict the overall reaction and the rate law in this case. Okay, so same type of question. They're just phrasing it a little bit differently. They're giving us a two-step mechanism here, and they're asking us to pull out the overall reaction from it and then to figure out what that rate law would be. Okay. So the first thing we're going to do is we're going to add these reactions together to find the overall reaction. All right, and this is going to be the same as last time. Anything that's the same on opposite sides of the arrow is going to cancel out. Everything else comes down as part of the overall reaction. So these are going to cancel out, and we end up with 2A plus B yields A2B. And that is our overall reaction. Okay, the rate law is going to be based on our slow step. So the rate is going to be equal to K times A squared. Okay, unlike a reactant that is part of an overall reaction, when you have a mechanism step, we are able to take the coefficient in front of the component and use that to represent the order of our reactant. You can only do this when it is a step in a mechanism. Okay, you cannot do this if you're looking at an overall reaction. All right, but because we're looking at these mechanism steps, we're able to look here and say, well, I have a 2 in front of the A, so this is going to be the exponent that gets attached to this particular reactant. All right. Our slow step is our rate determining step. So our rate law is going to be based just on our slow step here. So this is just a matter of saying that rate is going to be equal to K times the concentration of A squared. Okay, and that's going to be the rate law for our reaction. So it's not always complicated. If you had an intermediate that was part of your rate law, then we'd have to go through that same set of steps where we substituted in for it and then solved out for a different way to represent it, essentially. Okay, but that's it. I mean, those are the problems for chapter 15. So just keep on working through them. The more time you put in, the easier it's going to be on your exam day. And let us know if you have any questions.